that we can do, I'm going to plug this in, and before we start, actually, I'll just talk a little bit about what parallel processing versus concurrent processing versus multi-threading versus multiprocessing, all that kind of stuff. So the idea of concurrent processing or programming or computing is that you can have multiple, the same code or different code running at the exact same time on your computer using either different threads on your CPU or different cores on your CPU via processes or the threads. So why this might be useful is if you have to run the same code over and over again, why not just run it on, make use of all the multiple cores on your computer, because most computers these days come with multiple cores, right? So you can speed up your processing if you can schedule what you're running and you know exactly what's going to be running, then why not just run it on as many cores as you can that your computer can handle, and then leave it and then let it run, and then you can come back to your results, right? And it's faster that way. So Python actually has something called the global interpreter lock, which prevents you from actually being able to use multi-threading to achieve true parallelism. I'm not a complete expert on this, so I won't go into the details of that. But what you can do instead of multi-threading is use multiprocessing, which opens new processes on each core or each core to allow you to achieve some sort of without it being true parallelism. But that's kind of what we're going to focus on today. So for the first package, we're going to look at multiprocessing. It's a built-in Python package, and what I want you to do is just open some sort of Word text editor, and we're going to start a Python script just to get used to what multiprocessing kind of does. So before we get into any of the parallelism, we're going to look at this process function. So we're going to import. Everybody have their. Oh yeah, sorry, I don't know why that's there. Yes. So I'm just going to exit this for now. So I'm going to import multiprocessing, just like that. And I want to, right now, I'm just going to save this file as wherever you want to save this, as multiprocessing MP tutorial 1.py. Or you can name it whatever you want so you can access it easily. Okay, so I'm going to import multiprocessing. And then we're going to define a function that really doesn't do much. So we're going to call it a worker function. And it pretty much is going to do some work for us, which in this case is all it's going to do is print worker. And then it'll return nothing. So that's its job. It really just does that. So now I'm going to use an if name equals. So those are two underscores, name, underscore, underscore, equals, and I'll explain this in a second, why we need this. Main, underscore, underscore. Everyone see what that is? So those are just double underscores, right? So what this basically means is we have a script, and if I call the script by the name, and it's the same as the main script that's being run, I don't know if I'm describing this exactly, but if I'm calling this function exactly and not importing it, then this will run. If I'm just importing functions from this script, this will not run. So that kind of protects what's inside this code to only run if you're calling it directly. And this is, it's important later on, and I'll explain why. So we're just going to say jobs equals list, empty list. And then for I in range 5, we're going to send this to the multiprocessing function process. And the target is the function that we want to send to this function process. And our function is called worker, right? So we're going to just type in worker. So then jobs will then append whatever P makes. And then P is going to start. And that's all there is to the function. So let's go through what this does line by line. So we have defined this function worker. It just prints worker. And then we're going to iterate through 1 to 5, right? And then we're sending this process, this function to this process, which will run worker. And it will do it 5 times and append the result to jobs, right? And we need to start it at the end. So we've defined it here. And then we actually start the process here. So I'm going to open a terminal. So you can open your terminal anyway. I have one there. And I'm just going to cd to where I have, actually, do this a different way. So I'm just going to run Python. I'm going to save this first. Python MP tutorial 1. Use some tab completion there. If we run this, it'll just type worker 5 times, right? So that's a different process we're running each time doing our function worker. But usually we don't just want a worker function to be preset to do something. We want to give it inputs to. So this is kind of more basic programming, but we're just going to do it for the sake of any new people. So let's make a new function, a new script, which again, I'm going to copy and paste this beginning part. Now we're going to do print worker, but it's going to take a function. It's going to take an input. So let's give it a number. And I want to print worker and then the number. So it's at least taking some input, and I will show you how this can be set to the process as well. I'm going to save this as mp tutorial 2.py. Okay, so just like in the other one, we can have jobs equals, and since it's not really returning anything, this line is pretty much moot because it's not actually returning anything. Oh, it's returning none. But for this purposes, we'll have for I in range 5. Again, the target of the process is P, So P equals multiprocessing dot process. It's going to take the target, again, is worker. But now we can actually give it some arguments. And it always takes a tuple. So even if you're giving it one argument, you need to give it a tuple, one argument in a tuple. So I'm going to give it I for I in range 5. And then again, jobs.append P.
So you have to add that comment?
Yes. So a tuple is pretty much something enclosed in 2 brackets. And it can't just be one item or else that'll be executed as its own thing. The comma makes it a tuple. Yeah. And there you go. So we save this. And one thing to note is that this won't necessarily output in the red. So what we would expect is to see worker 1 or 2, worker 3, or 0, 1, 2, 3, 4, right? Let's see. So this actually comes out in the right order, but because how it's sent to, right? How it's sent to the CPU, it's not necessarily always done in the same order. It'll kind of just send out kind of randomly these processes to the core, and maybe won't always go out in 0, 1, 2, 3, 4, 5. So you have to keep that in mind when you're sending a process in this way. Okay.
This one actually did go.
Yeah, exactly. Oh, it did? I can't see.
Yeah, 0, 1.
Oh, I see. Yeah, sorry. So yeah, this one did go out of order. And so if you're expecting that your results come back in the same order, you need to have some sort of tag to then sort them by.
Okay. I just keep running it over and over, and it keeps doing it in order.
Okay, I'm not sure why.
Maybe make the range not larger. I'm done.
I think it depends on how specifically your system will do it.
It's an indeterminate process. So
okay.
Sometimes it'll be order, sometimes it won't.
See.
There's no guarantee.
I see. So sometimes it does go in order.
It does the same.
Okay.
It might do the same over and over again, but it might not. The part of the spec is that the order is not. It's like with dictionaries. You can't help.
Right. Yeah.
And even though now in modern Python they are ordered.
Yeah. Yeah. Alphabetically. Yeah. Okay. So now that we kind of have a general idea of how that process works, we're going to actually look at how to run things in concurrently. So we're going to use some multiprocessing submodules called pool and map. Actually, just pool for now. Multiprocessing import pool. We're going to use some other submodules just to keep track, just to give us more information about what. So these are current process and CPU count. So I'm just going to import those. I'm going to save this one. as MP tutorial 3.py. Okay. Okay, so I'm going to define a function again, but this is actually going to do something a little different, I guess, just to be a bit more useful. So we're just going to take x in this function f, and we're going to multiply it by 2. So we can even call this double if we wanted to, just to be more specific, but for now we'll call it f. And we're going to start process, which will just tell us what the name of the process is and tell us that it's starting. And we can do that using an initializer later on, which I'll show you. So I'm going to print, I just need to do something to make sure this is all Python 3. Sorry about the, okay. So we're going to print starting. I'm going to use the current process module. It'll print us the current process right there. Dot name. That'll just give us the name of the current process that's working. And then we're going to run our if name equals main. So the reason we want to keep this in an if name equals main is because if we put this into the main block of code, outside of this if name equals main, then anytime we import this, import any of the functions here, it'll keep spawning processes, and like the way that multiprocessing work, you won't really be able to control what it starts doing at that point. It's just best to contain it in here, keep things CPU safe or multiprocessing safe in a way. Okay, this is very important. Okay, so first we're going to have some inputs that we're going to give to our function. So let's just make a range of 10. And then we're going to print what the inputs are just so that we know. And then we're going to see what the built-in process would look like when we just use Python's map function. So let's map f of input. This is just a built-in Python function that will map your inputs to almost run a for loop pretty much over your function. So it's just like the built-in. We're going to compare our result to the built-in to make sure it's working. And now we're going to be able to actually build our concurrent computing part. So we're just going to start by number of cores to use. We can do that by doing the pool size is equal to that function we have up at the top, which is CPU count. And it's just a function built into multiprocessing. And then we'll just print that so that we know. Okay. And then the part that we're probably most interested in is this pool function, the capital P. It processes, tells how many processes we want to run concurrently. So we're going to put in pool size. So it's going to, what pool CPU count will do is count how many CPUs I have on my computer available. Or I don't know if it's available or in total. I think it might be in total. And then I can use that to then inform how many cores I will use. Put that in there, pool size, and an initializer pretty much just says like something that you run at the start of a process. So we've already defined this start process, which will then run starting process name, right? So we're going to put in start process. And then now to use pool. So pool is using the pool of the class from the pool function. And then it has this a method called map, which will then map the function f to the inputs. So it's just like a Python map, which is the built-in function, right? Except this is going to run concurrently as opposed to serialized in order. So this, yeah. All right, so let's just save that. And we're going to run this. Python MP tutorial 3.py. So, oh, sorry, I forgot to write what the outputs are. I'm going to continue editing this. First, we also need to close the pool when there's no more tasks, and then to wrap up, to wrap up the current tasks, like these two things. Can't remember exactly why there needs to be two of them, but they make sure that everything's closed. If there are processes still running, they're done. And then we're going to print the output. Pool.nav. I'm going to save this to pool outputs equals. I'm going to print pool results in pool underscore outputs. So we're going to compare the built-ins to, okay, let's just do this first. Okay. So it was able to start those 4 processes all at once and run that all at once. So if we compare that to the built-in, so I'm just going to have a print just to make, I mean, we can also tell that 0, 1, 2, 3, like to 9 times 2 is 18, but we can also compare it to the built-in output. Yeah, so these are the built-in results, and there are these results. Okay. So the main point you want to remember from this is that you use this pool function to initialize the pool object, which will tell you how many cores you're going to use. And then importantly, you'll take that pool.map to map that function, to map the inputs, which are defined here, to this function, just like a Python map, except now it'll run on all the cores that you've told it to run at the same time. Okay? Does anyone have any questions about this part? Yeah.
So in practice, do you want to use all the cores in the system? Or
it depends if you will be using those cores for other things. If you need to use your computer, you might want to save like a few cores for your own personal use, like if you're running different, like your browser and stuff like that. If you're not really doing anything on it, I wouldn't say like, why not use all of them? Yeah, so in this case, we are using, and especially if it's not hugely memory intensive. I mean, this was a very not memory intensive task. If you're doing really memory intensive tasks, then you probably wouldn't want to be doing other things on your computer at the same time that require multiple processes. Yeah, so you just need to think about how much are other people using it, like if it's a shared computer, that kind of thing. Yeah, okay, so this is, that's pretty much you can do, if you have a function that will take one varying input, like it takes really only one parameter, and you need to run it with different versions of this parameter or multiple times on this to make sure that your function is like consistent and things like that, just to see, then this is where you would use the multiprocessing pool. But what if we have a case where, actually, I'm going to show you another package that can do the exact same thing, and I'll show you how that package can also expand on that. So this new package we're going to use is called joblib, which, does anybody here not have joblib installed from the instructions? Okay. So do you have access to the internet right now? Okay, so you can probably pip install joblib, so it's like joblib like that, really quickly. So what I'm going to do is I'm going to open a new file, save this as joblib tutorial.py. Okay, so let's try to recreate what we've done with the map function, with the parallel pool submodule in multiprocessing using joblib. So from joblib import, these are the two important parallel, delayed, and again, it has a CPU count too, and I think it might actually be from multiprocessing. It uses some of the multiprocessing backend, but does some other interesting things too. So what we're going to do is define the same function, define f of x, and return the double, right? X times 2. And then if name, I'm not really going to do an initializer because we're not going to really use that right now. I've already shown you what that can do. Equals main. Again, joblib requires you to have everything safely packaged into your if name equals main, because again, child processes can spawn, and then you're going to quickly end up with like no CPUs left to use. And then you have to go back and close all those, and then, yeah, anyways. So what we're going to do is going to have our inputs again, just like before. Inputs equals list range. I think this package was actually built either by or for users of scikit-learn. So this is actually widely used by a lot of people for machine learning and for non-machine learning purposes. But yeah, and you see a bit of an example of that later. Okay, so we have our inputs. We're going to do our built-in input output just to make sure everything looks right. Again, map path and inputs. And we're going to just print that so we can see it. So this is how joblib does its work. So it'll basically do, so let's see. So let's put output equals parallel. So parallel just tells you that we're going to be using the parallel module, and then you type in n jobs, the n jobs parameter, which is the same as that the pool size that we were talking about before in multiprocessing. This tells you how many cores we're going to use or processes we will use. So again, I know I have 4 cores, so I'm just going to put 4, but we could again use CPU count. Actually, let's just do that for consistency. Pool size equals CPU count. Okay. Full size, and then it kind of has this weird looking aspect to it. It returns another function which we can then give the parameters to, this delayed, which will be the iterator pretty much. So it has this weird looking syntax where it's like parallel and then the brackets, but then another set of brackets where you put delayed inside. So inside the delayed brackets, we'll give it the function we want to run, which is f. And then beside that, we'll give another set of brackets. So it has a funny looking syntax, but we'll see how it can be useful later on. So we're going to give it x, and for x in range, x in inputs. So we can see that this whole part tells you what we're iterating over, and this part just tells us how many the parameters of the parallel, right? Okay, so then let's just print the output. See how this goes. So Python and then joblib tutorial. Okay, so it gives us a nice result that we expected, and it's exact same. It's pretty much, in this case, it's doing the exact same work as multiprocessing, so there's no benefit, right? Where there is a benefit is what if you have to give multiple arguments to a function that change, or maybe some don't change, but you need to give arguments that aren't just one argument, right? Because multi actually only is able to take one single argument through this map function. And I'll go back in a second, but there's also, you can use apply as well, pool.apply. Pool.apply will do the same as the Python apply. Anyways, this can only take f and take the inputs. It'll iterate over those inputs as if those are the only arguments to f. So let's look at an example where this works in multiprocessing. So let's say we have from joblib, we're going to also import parallel again, delayed, and CPU count. We're going to define a function that takes 2 arguments. Return let's multiply x times y, right? So if name, I'm going to save this first as joblib real 2. Okay. So we're gonna set y to something consistent. We're just gonna set it to 2, but then our inputs are gonna change, which are x. Let's just call this x values. And then we're gonna print x. So if we do our built-in output again, it would pretty much be f times x comma y for x in inputs. Some with comprehension, right? Then we're going to print those built-ins, outputs. Sorry. Now we're going to see how, I'm just going to write pool size equals CPU count, and then we'll see how this would work. So outputs would be that parallel part again, and we're going to tell it to be the number of jobs we want it to do is equal to our pool size. And we're going to take that delayed of f, right? Because that's the function we want to run it on. We'll take x. And we'll give, so the next, so this set of brackets that comes after the delayed of f tells us all the parameters that will go into f. Either in the order, or you can name them. You can have them like this, x equals x, y equals y. In this case, we call them I and j, because it's just gonna, well, y needs to be y because I've said it earlier, but we can call that I, and then do for I in inputs. Okay. So over here, we have the function we want to run, the parameters that go into this function, arguments that go into this function, either named or in the order that they should appear, if they're unnamed, and then for the iterator that is going to go into it. Yeah.
You haven't not called inputs, it's called x.
Oh, sorry, yes, I'm just thinking to what we've done. Thank you. All right.
Same on both, yeah.
All right, cool, thank you. Yeah, thank you. X dots. And then we can print parallel result both outputs. All right, so this is saved, and let's run this Python -2.py. There you go. You could almost see that there was a bit of a pause before printing the built-in, and then no pause going for the parallel results. That was pretty fast, maybe we didn't notice. But yeah, so in this case, we're able to give it a parameter that maybe we have another function up here that will produce a result, and we need that result to plug into here, right? And it's not necessarily going to be a default all the time. It depends on what we're inputting to this function. So that might be useful. But what if we have x and y varying, and we know what those will be? And we want to say we have two parameters we want to vary, and we want to vary them together or apart, and then input them into this function. So what that might look like is, sorry. I'm actually just going to edit right in here. So let's say we don't have y equals 2. Y can also be something else, multiple values. Equals list range. Let's just do 10 to 20. We'll make them the same size, like 10 values each, but just different values. Print x and y. Okay. And then in this case, the built-in would be x comma y. And actually, we might need to, let's just zip these together. Yeah, for this purpose, we will have to zip the x values and y values together. That's equals And then we'll do that. Okay. Instead of this, we will print inputs. Okay. Now the built-in will be XY for XY in inputs. And then in this case, X and Y, again, could be I or J or X, like any letters you want, because they're just dummy variables, right? I and J in the tuple, the zip values, inputs. So what we've changed is we've made a new set of variables for Y. We've zipped them together so that now they look like, you'll see in a second that they're just tuples, right? And then now you can iterate over each of those tuples and you get two parameters that are changing. Those will be input to the function here, function f, and then they will run on the number of cores that you've specified. Let's run this again. There you go. That's the result. So that's pretty much what you can do with it's just, if we want to go over what we've done in this lesson so far, it's pretty much how we can deal with for loops parallelized, right? Because otherwise we could have done this using for loops. But for loops are obviously long, and like if we just need to run something multiple times, why not just run them on as many cores as we can and get it done, right? Yeah.
Just going back, what's the advantage of doing this very simple?
So multiprocessing doesn't allow you to have two varying arguments, and then also even to specify other arguments to that function, right? Yeah.
But you could still use something with multiple arguments.
If they're predefined.
Or you're just varying over multiprocessing.
Yeah, right. If only one thing is changing and the rest you can somehow like default to the, like a function can have multiple arguments and not have those arguments change, right? In this case, if we do want them to change or be given in the, not prior, but because of other inputs that are being given to the function, then we would use joblib, for example, yeah. But yeah, that's a good point. Okay, and then just as a last example of like, so open. Okay, maybe I shouldn't do this. Does anybody here use distributed processing, you know, using multiple computers and the cloud pretty much? You know? I don't either, so this example is going to be a bit over my head, but just kind of to show you that how easy it is that to use joblib in terms of scikit-learn packages. I'm just going to show you some of the one very simple example of how you can use it, for example, in hyperparameter optimization. So that basically means like when you have a machine learning algorithm, there's many parameters that you might want to optimize, right? You can manually do them, just like plug in one and see if it does better. But if you just want to be able to explore them in a very, what's the word, like systematic manner, and then see what the results are, then that's requiring a lot of computational power. And of course, you'd want to then, in cases of high computational power, you'd want to use as many cores or do things distributed on the cloud or things like that. So this is one of the times when this is very useful to split up your work. So what I didn't tell you guys to download this, but it's the Dask distributed package. Dask specifically is for distributed computing, and then it has this. It can use joblib very well, and specifically for scikit-learn. So we're going to import distributed.joblib, and depending on how you downloaded or like what packages your scikit-learn or your packages, you need to import the parallel backend, which is what does the parallel work, through scikit-learn or through joblib itself. But I think for me it works just to do scikit-learn. So from sklearn.externals.joblib. So here I'm getting this submodule of joblib from an sklearn version of joblib. Import parallel, backend, and then from SK. I'm just going to download a data set or get a data set from sklearn. Import load bits on sklearn.grid search. Import random. So this is just a way to, it's sklearn way of parameter searching. It's a parameter randomized search CV. And then we're going to use this for vector machine, just for the purposes of this. You could use anything you wanted. And then just import. So I'm just going to load the digits. So first I'm going to just run all these. Or maybe I shouldn't have done that. Sorry. Okay, so you can ignore that. We set up our parameter space for the parameters that you're interested in. So in this case, the example shows the C value for NumPy. We can go from various numbers by 10. And then let's just say gamma. And I'll keep it short there because it probably isn't that fun to watch. Okay. And then we're going to create the model. Sorry, I don't know why I keep messing that. So the model is SVC kernel. So these specifics don't really matter. It's more about how you're going to use your own machine learning algorithm and that you want to search. So we'll just take the model, the parameter space, CV equals. So these are less important. And the number of iterations, for example. Okay. And then, so that's just setting up the model. You've set up the parameters, you set up the data you're going to use. And then to use the parallel backend, it's literally 2 lines of code where it's just using parallel backend from that joblib package or from sklearn's parallel backend. We'll tell it that we're going to use dask.distributed. And then you're going to tell it where the server is. In this case, it'll just be a local host. I don't know that this, I didn't test that this could actually run in time for us to see the results. But let's just say it's that. And then, so with parallel backend, and then you're telling it the information that it needs to know, we're going to give it the search.fit digits data and digits.target. Okay. And I'm going to save this as a Dask tutorial, or sort of, yeah, .py. If I did everything right, this should be okay. But let's say Python. So as you can see, it's whether this runs or not. This is the straight example from Dask and scikit-learn and joblib themselves that just show it's very simple, short. Let's just see what we can get from this. Oh, gamma. I think I'm missing a comma somewhere. Yeah. Okay. Oh, I think that's just because I have some deprecated modules, but seems to be running, but I don't have any errors yet. Anyways, so the point is that I think there's many packages now that can use that, even though Python has this global interpreter, global interpreter lock that prevents you from necessarily doing truly parallel, speaking to each other type of programming, computing. There are ways around it because oftentimes what we really need is just things to run at the same time, not necessarily speaking to each other, and not necessarily being exactly parallel, right? Just good enough for it to be pretty much parallel, pretty much concurrent. Yeah, so if you have any questions, you put your hand up or just ask. Yeah.
Could you bring up a terminal with HTOP?
HTOP.
HTOP. It's shows all how much.
Oh, sure. Yeah. Let's see. I don't have it installed. Do I have to? I can try. Install htop. Isn't that the same as top? Like when I just use top 2?
Htop is a lot better. So it's,
Okay.
Htop will actually show you parts of the.
Oh, okay.
Let's see H. There are a few different Unix things with H in front that have been upgraded in some.
Whoa, is that any good? So what's happening?
100%.
Yeah.
All the cores.
Yeah. So I don't know if you guys can see, but yeah, I'm gonna try to make that. How do you make this bigger? I'll put in the center. Yeah, so it's using 100% of pretty much my 4. Except, well, 4 processes, let's say.
Yeah, and most of it's being used by.
Yeah, most of it is Anaconda. Yeah, exactly. So yeah, it's working. It probably won't finish in time for us to see the result, but yeah, there you go. And I think if you use a local host, it'll automatically know how many cores to use. And like you don't need to specify, but you can specify if you want to.
Do you have to actually run that scheduler in advance? Like, do you have the schedule host?
No, I just know this one is available because that's what I use my Jupyter notebooks in. But I didn't actually make that ahead of time or anything like that. Yeah.
You didn't have to go to.
No, I think by default it will use your, if you don't, the scheduler hosts, if you give it that like empty port that's typically not used, then it can then just run. Yeah. You can then obviously give it a non-local host like Amazon cloud type computing thing or whatever you want to give it, right? So yeah, and that's pretty much all I planned for the day. Yeah, so personally how I use this is I have access to the SciNet cluster, and because I do similar machine learning but except not using scikit-learn, and what I'll do is I need to parameter search, and what I'll do is I'll set it up so that I can send to the, I mean, SciNet requires you to use up all the cores in a single node. So you can't send it just a single process. They will be very mad at you for wasting their resources. So you have to, for those purposes, you have to be able to split up your code into these multi-processing type things. So that's kind of personally how I use it, but I know many people make use of multiple cores at once or multiple nodes at once in the cluster and get a lot done. It's a good resource if anybody here is interested in learning about SciNet. They have okay documentation, but they're very helpful if you email them. Anyways, that's all I have for the lesson.